Yeah, thanks Rafa for the introduction. It's a great pleasure to be able to present this work here. So it's a, oh, sorry, I need to learn this. So it's a joint project with Marcin Kotowski, Michał Oszmaniec, and Marcin Kotowski is from Center for Theoretical Physics, Michał Oszmaniec from Gdańsk, Nick Hunter-Jones from Stanford and now Austin in the United States. Yeah, and I will be talking about saturation and recurrence of circuit complexity in random quantum dynamics. Yeah, and basically my talk will be like a meditation about this diagram that you see here. I will explain what it means, yeah, in what follows. Right, so let me start with just setting up the stage and notation. Yeah, so I want to define notion of classical and quantum circuit complexity. Right, so let's start with classical complexity. So let us imagine that we have a like system of n bits, and we want to realize some reversible function, that is to say reversible transformation of those bits. So this guy like takes n bits as input and spits out another collection of n bits. And we want to build it from some primitive building blocks, namely elementary gates. So imagine I have on my disposal just some local transformations that can act on at most, say, 2 or 3 bits at the time, like reversible ones. And now, yeah, I want to circuit complexity of this function is, yeah, basically the minimal size of a circuit built from this this collection of elementary gates. Yeah, good. So this is classical circuit complexity. Now moving to quantum complexity. Reversible function is now replaced. Set of n bits is replaced by collection of n qubits. Reversible function is replaced by some unitary transformation that transforms states on those n qubits. And now I don't have reversible classical circuits, but I have just some primitive elementary gates that I apply, that are still local, so they act on just like at most constant number of qubits at the time. And again, circuit complexity of this unitary now is the minimal size of the circuit built from those elementary gates that realizes this unitary. Okay, now up to certain precision epsilon. The precision epsilon comes from the fact that the set of all unitaries is a continuous manifold, so we need to have some discretization of it. So I'm not going to dwell that much on the notion of distance that I'm using here to set this precision, but to expert I'm just using Diamond norm. So the vanilla, the golden standard distance between unitaries. Good. And yeah, needless to say, those notions, classical and quantum circuit complexity, they have, play predominant role in computer science, quantum information. So, for example, when you define those basic complexity classes like P, BPP, or you use basically classical complexity, right? So basically problems that are solvable efficiently on the classical computers are the ones that for which complexity of a function that solves those problems is polynomial with the system size. And the same for quantum circuit complexity. So complexity class of BQP. So problems that can be efficiently solved on quantum computer is captured by unitaries that have at most like polynomial circuit complexity. But outside of the field of quantum computation, also people study this, say, quantum circuit complexity in the, for example, when they want to classify phases of matter. So, you know, when you have two phases of matter, we say that they will be like really distinct if relative circuit complexity of moving from one to another is large. If this complexity is small, then it's basically the same class, perhaps. What else? And yeah, people were interested also in this quantum complexity in the context of like evolutions of strongly interacting quantum systems. And I'm gonna move there later. So now one message I want to convey is that computing circuit complexity is a really hard problem. And I want to illustrate it on a very basic example, namely rotations about some angle alpha on a circle. So it's a very like basic example. I pick my fundamental gate set to consist now of just identity transformation and rotation about angle alpha. And now I set some tolerance epsilon, okay? And of course I can, when I compute, you know, I compute k-fold rotation, like concatenate k times rotation by angle alpha. Of course I can bound its complexity by k. But eventually, let's say if this alpha is not rational multiple, yeah, eventually I'm gonna get close, I'm gonna get close to 0, okay, for some k equal to k star, and then my complexity would be 0. So I have growing complexity, and then it drops, right? So I have, because just identity transformations approximates very well my gate that I wanted to implement. So I have possible shortcuts of complexity, right? So just circuit prescription gives me typically some upper bound on the complexity of the unitary, but I can have some funny shortcuts that I, in general, would need to avoid. Right, so this is the issue. Yeah, in general, what I want to say here, that it's, there are some complexity theoretic arguments that it's, in general, like hard to decide what is hard to compute the complexity of a given circuit, even classical one. You can place this problem in like second or third level of so-called polynomial hierarchy, so it's even above NP. It's a hard problem. Right. Nevertheless, we want to study some aspects of it. Good. And I should say, of course, when you design some quantum algorithm that maybe solves some useful problem, you would want to minimize the circuit complexity. So just for example, was it last year? I think people improved circuit complexity of implementing Scholl algorithm or factoring algorithm. So yeah, circuit complexity is an interesting quantity that you should care about when you care about quantum computing. Good. Now, yeah, let me move to the subject of my talk. So. Brown-Susskind conjecture. So the setting is the following. Imagine I have a system of n qubits that, or n particles that strongly interact. I don't want to specify that much what I mean by this, but this Hamiltonian age shouldn't be integrable, for example. Yeah, and I want to now, okay, I have unitary like evolution operator that corresponds to this, like to Hamiltonian of the system, and I want to trace how how complexity of this unitary changes with time. Yeah, those two gentlemen from States, Adam Brown and Lenny Susskind, they couple of years back formulated the following conjecture for how like complexity of this unitary should behave. So we have in general 3 phases that like repeat in time. So first we should have linear growth for exponential time. After exponential time, we should have saturation of this complexity at exponentially large value. And now for very, very long time, double exponential time, we should have this large value. After this time, we should exhibit a recurrence of complexity. We should then go down with complexity to 0, like in such a dip. That should have exponential width. And then you repeat. So this is the conjecture. Maybe let me comment this linear part. It's probably the part that captured the most attention. I'm gonna comment on that soon. But like basically, just quantum. Like if your Hamiltonian is local, so you have it's a sum of terms that couple at most say 2 or 3 qubits at the time, or constant number of qubits, just compilation algorithms, the best, say, quantum simulation algorithms, have complexity that is linear with t. So when people want to simulate quantum evolution on a quantum computer, they cared about minimizing the gate complexity, and the best algorithms have linear complexity. But now we want to, like what this conjecture asserts here is that we have also lower bound, which is linear with t. So no free lunches, no shortcuts to complexity in this earlier time. Now this saturation just comes from the fact that, okay, we have a set precision epsilon, and just there is some absolute upper bound on complexity that you can reach in your system. So it's gonna grow, but like eventually you just some brute force compilation algorithm would just allow you to have to bound the complexity from above. Right. And
so it's like a really maximum value. So like
yeah, or like
the complexity of every unitary. I mean,
yeah.
Maybe if epsilon goes to 0, then this goes up.
Of course, yeah. So I should say that those guys are like brilliant physicists, but they come from more like high energy physics, gravity side, and they were not very like formal when they formulated this conjecture. So it was very, to us and other people, very inspiring conjecture. It still is, but they're not very like, you maybe shouldn't be like so precise what you mean. Okay, especially, just when you take this circuit complexity, it depends on the choice of your gate set as well, right? So you can translate between like complexities with respect to different gate sets. You have some polynomial overheads. So from that perspective, this this picture like just becomes blurred, right? Because like you should think more like as like equivalence classes of complexities, if you want. So exact values don't really matter that much, but just qualitative behavior matters. Good. And that was a crazy thing because I don't really understand it still. Even though I interact with people from this community, so they formulated this in the context of so-called ADS-CFT duality, which is, as far as I understand, conjecture duality between quantum gravity in anti-de Sitter space-time and some conformal field theory which is defined on the boundary of this space-time. Okay? And now you have, how is it? Like you have something like two ADS space-times like this. You connect them via wormhole, so you have another like space-time. And then you can run Einstein equations, and you see that like size of this wormhole just grows with time, okay, for a very like long time. And now those guys, they are interested. Okay, so this is on the gravity side, on the anti-de Sitter side. So what would be the corresponding quantum quantity? So people studied, I don't know, entanglement, some features of scrambling in the past, but those things, they grow very fast with the system size. They saturate after essentially linear time. So that's why Rennie had this mind-boggling idea that, yeah, this complexity, circuit complexity should be dual to, I don't know, size of this wormhole in some sense. So that's how they think about it. And for example, this dip of complexity should correspond to like evaporation after a very long time of like, I know, like white hole that then originates later on. Okay, so that's their motivation, but personally, it's very crazy.
What is n in their case? What is n?
And so I think it's like n. So n is proportional to like surface of like some surface of like band of wormhole here. Okay, yeah, like and yeah.
This is the many-body Hamiltonian on the border, right?
Yeah. Yeah, okay, but don't ask me more about it. It's maybe a source for nice mathematical quantum information questions for me. I should maybe say that, yeah, from many-body physics perspective, it's also just nice to be able to pinpoint universal properties of systems, like different classes of systems, how they behave, right? So I think like this is quite. This is the feature of strong interacting system that typically one should exhibit. Like if you don't have integrability or you're not in some low dimensional manifold of your unitaries because of, I know, free fermions or free bosons or something like this. Okay, so this is a very hard. This is interesting but a hard problem. So people. At the moment cannot address Hamiltonian evolution, so they resort to studying simpler models, namely models of scrambling evolution based on random quantum circuits. So they are, yeah, defined as follows. So now your unitary after time t is actually just a composition of t unitaries that are chosen at random. You know, from you randomly pick two qubits and you couple them by some local gate chosen at random. And there, the same conjecture so now depth of this random circuit is plays the role of time, and you have the same conjecture.
Random two local gate applies to random pair of qubits.
Yeah, the details don't matter actually that much. It can be k-local. Yeah. I will define later more formally what is the model that we study. Okay, and you have the same conjecture. And what is which is now much easier to analyze because you throw in randomness in every time step. And typically, if you don't have a structure and you don't have insights, you can all you can do, you can rely on randomness when you have complicated systems. yeah, so people were able to some extent, prove some aspects of this conjecture. So, over 10 years ago, there was a paper by Brandao, Harrow, and Michał Oszmaniec. They studied they proved that random quantum circuits form so-called approximate T designs or K designs, and you can use those results to prove early time algebraic growth. Not linear, but algebraic growth. 2 years ago, Jonas Haferkamp from Berlin, now Harvard, and collaborators studied simplified notion of complexity when you take epsilon equal to 0, so just exactly zero error. They use some techniques from algebraic geometry to prove this linear growth, okay, for exponential time. And earlier this year, it was sort of like a breakthrough in on the side of mathematical analysis of random quantum circuits. And again, Jonas, Robert Huang, and co-authors, they proved actually, now for the physical notion of approximation, linear growth of complexity for some exponential time, maybe not all the way to the saturation time. Yeah, it's some nice piece of mathematics, yeah, from a couple of months ago. And where our work sort of enters, so it concerns this saturation, recurrence, time aspect. So we prove that indeed you, like after exponentially long time, with this dependence on epsilon, you would saturate on value of complexity which is essentially maximal. After double exponential time, and we have explicit dependence on epsilon here, with high probability your complexity will drop to 0. And lastly, the size of this window is of exponential order again. So this is like aspects that we cover in this work for random quantum circuits, as well as some other just cousin of this model, namely stochastic local Hamiltonian models, which is basically the model when your Hamiltonian just fluctuates in time, but it's still local, okay? And you have, it's like effectively like a local Brownian motion in the space of circuits.
So in this T recurrence, this
yeah.
e to theta n is in the exponent.
Yes, so it's double exponential in the system size.
So it's 1 over epsilon to the power.
Yes. Good. So this is the scope of our results. In what follows, I want to explain, sketch how we get them, but either at this stage, any comments or questions?
So, can you tell us maybe what is the intuition behind this value for this long time?
Size of this value or the...
Why it appears?
Right. So maybe it will actually, I'm tempted to say that it would, the intuition would be that, there is some nice intuition in the idea of the proof, but basically it's you can say Poincare recurrence time, okay, and So basically, because eventually your random walker should come back to the origin, let's say. So that's the intuition.
Yeah, but I think the question is about the size of this value.
The size of the value. Right. So the size.
But it's the same as initial size.
Yeah. The size from the right is sort of similar. Okay. So let's say you have some sort of in the definition of this model, you know that your complexity shouldn't like cannot change that much with time because you change your gates, your unitaries, by applying of local gates. So this is like the like if something changes, it at most can change linearly with time. Okay, and to get from exponential complexity to zero complexity, you need exponential time. That's, I think, okay. Good. Let me proceed.
So I wanted to ask you
Yes.
this Hamiltonian, because you said it's local.
Yeah.
So this Hij is what it's a two local Hamiltonian. So
Let's say two local can be also generalized. Yeah, two local. Let's say all to can be all to all, can be on a line.
okay, so just to understand, in every step, I have a set of Hamiltonians, or I have a...
So it's like so you have like in every step you have those guys, but maybe okay you have some random variable psi ij, right? So this is Hamiltonian at time t, right? Some ij. Let's say everything couples to everything, and then you have let's say you evolve by time, say delta t. There's h of h of t, and you have this psi I, like psi k l is like 1 over delta t, and then so you take such. So this is maybe in time ti, okay. And then you take like a product of them, and you take the limit. So it's like a just Brownian motion of the.
Is that like Langevin normalized?
Yeah. So it's like just like Langevin evolution, but in the space of unitaries. Yeah. So it's just actually the technical contributions like Marcin at some point added this model to our paper, and he joined the paper, and this is what made us publish maybe higher. But like I'm not going to talk about it too much. So that was from less than a year ago. So that was new parts. Yeah. But I'm going to focus on random circuits. Good. Is it really necessary that I'm going to go past this? So, right. So just formally, my unitary after t steps is taken from, is a product of unitaries that are taken independently at random from this ensemble mu g. Let's say this G encodes the graph of my connections. So I'm choosing in every step pair of qubits at random, and then I apply random gate like gate on 2 qubits. And formally, I'm gonna then after t steps, those unitaries, they are just distributed according to convolution of this measure after t steps. And now, what is on high level might be important is that those random ensembles, they form so-called k-designs or expanders. That was analyzed in earlier works, and maybe connecting to some media buzz this week when you hear random circuit sampling, you sort of have relatively shallow depth, but this type of structure where this graph corresponds roughly to the layout of Google, in this case, device. Okay, right. And now, technically, technically, what we end up using is spectral gap of transition operator that corresponds to measures on the unitary group. Sorry, I shifted from, I will now just introduce some formalism, then I hopefully give intuitions. Okay, like how we prove those things. So yeah, we have this measure on the unitary group, and now, you can think of it that with probability, with different probabilities, you're going to transform, say, identity transformation to different unitaries according to your measure. Okay, you can now like use this measure to act on functions. Okay, so just to translate functions on the group. So those are formal integrable functions on square integrable functions on the unitary group. Good. And now we say that this measure has a spectral gap delta. So we have a measure, but basically we will get full mixing if we had a higher measure there instead of this measure nu. So you want to compare how close this operator, this transfer operator mu is to the corresponding transfer operator for the higher measure. And when we take the difference and compute operator norm, like basically, and if this thing is upper bound by delta, we'll say that we have spectral gap like 1 minus delta of this, okay? And actually, just probably literally tomorrow in my lecture with Marcin Kotowski, we are gonna talk about those approximate expanders or designs, so you can relax this notion to look on k polynomials of degree k, and you have approximate k expanders. But this is stronger property. And basically all we need from this like mathematical mumbo jumbo is the fact that in the literature of random quantum circuits, you do have some crude but for us fine bounds on those spectral gaps, which ensure relatively fast convergence of those transfer operators to each other. So both for random quantum circuits and for stochastic local Hamiltonians, the spectral norm where I evolve with time here, okay, both models, decays exponentially with time. Okay, but I have this thing in the denominator that slows me down, and it's dimension squared. So as soon as I'm above dimension squared, I will be very fast converging. Okay, and now I can,
Capital D.
Capital D is the dimension. Oh, yeah, it's a dimension. It's the small d, sorry.
So capital D is small d.
Yeah, sorry. Yeah, that's usual mistake on my end.
C is
some absolute constant. Yeah. Okay, and now just bear with me for a second. The key property that allows us to prove all those properties, saturation, recurrence, and duration of those recurrence phenomena, is something we call approximate equidistribution property. So it's some notion of approximation of higher measure on discrete scales. So now, let mu be normalized higher measure in my unitary group. Let's consider ball of radius epsilon around some unitary v. And let this vol of epsilon be just the higher measure of this ball. And now it's a common knowledge that basically volume of this ball is exponentially small with the dimension of the space. Okay, so we have those bounds. Okay, and now let me now consider another measure, not higher measure. Let me fix parameter epsilon and some parameters alpha and beta. Alpha is smaller than 1, beta is larger than 1. And basically, I'm going to say that this measure is approximate, is alpha beta approximately equidistributed on scale epsilon if measure that it assigns to the ball of radius, of radius r, it should be, of radius r, is comparable to measures of 30 larger and 30 smaller balls, volumes according to higher measure. So on scale epsilon, or at least, at most, like on scales epsilon, I basically agree, I assign right volumes, okay? Right. And that's basically the key property that we use in our proofs. that some measures would gonna like equidistribute. Okay, what is, yeah.
Just for students and myself, is it
Fair.
is easy to say that the trick is that you look, I draw, because it's about drawing, random drawing from the space, no? If I draw a point,
Yep.
basically around this point there is a volume, this is your kind of trick, that it would be equivalent to be drawn from Haar measure.
Very good. Yeah. That's the exactly. So functionally, yes. Yeah. So but on scales epsilon. This is like so from perspective of analysis of doing some counting, taking volumes on scales epsilon. I'm like as if I had Haar measure. Yes. Very good. Yeah. Thanks. I will use it sometime later when I explain it. Good. So what's the structure of our results? Let us assume that some like measure after time t, after some time t equidistributed, really equidistributes on some scale epsilon. Okay, and now just from that, we get that with high probability, complexity of those unitaries is large, okay, like is close to maximal for times that are above equidistribution time. We get that with high probability, if I trace my Walker and compute its complexity, it's gonna drop to 0 after this recurrence time that has really this scaling 1 over epsilon to the power d squared. And lastly, I can argue that duration of recurrences is of order t equidistributed. And now, just so basically, what we only technical part is that we can show that we can relate this gap condition or the spectral this bound on operator norm. We can enforce some conditions on it, like when this quantity is very small, we are gonna be equidistributed. Okay, so this is some technical thing we need to prove. We just combine it with this decay of this expander norm to get bounds like on equidistribution time for our setting for random local quantum circuits and for stochastic local Hamiltonians. And in both cases, those bounds, they scale like exponentially with the system size and log 1 over epsilon, with the regularization parameter. And so on high level, this is it's actually nice that we can just now use equidistribution property together with those black box results to get our claims. Okay, so in what follows, I basically want to maybe give sketches of those two results. So on high level, like just equidistribution alone allows us to assess that we are going to have saturation, recurrence, and duration of recurrence after the and the results depend on this equidistribution time, and then we use results from random quantum circuits to give bounds on this recurrent equidistribution time.
So this equidistribution occurs independently of the gate set?
Roughly speaking, yes. So you have those spectral gaps for basically any connected graph. Like as long as you, And they are basically up to some polynomial factors that perhaps I should say that I hidden some minor dependencies on gate sets that are like polynomial. Yes. That's. Yeah, it needs to be universal.
Okay, because I can intuitively understand the saturation and so on, but I still cannot grasp this
Recurrent.
recurrence.
Yes,
Not
good.
From random unitaries at all.
Yes. I have a sketch because actually the formally it's not maybe It's not complicated, but it's a couple of lines, or like 1.5 pages or something, but I have some intuition for that. Okay, but I still, maybe I start with the saturation first, okay, because for students and, right, saturation. Right, so let us just fix some universal gate set that defines complexity, and now, yeah, basically we claim that with high probability, if the measure nu equidistributes on scale epsilon, then complexity of randomly chosen u from this ensemble will have the following lower bound. Okay, and you have here dimension to the squared, which in the case of n qubits, it's 4 to the n. Okay. Right. I have some fine. Forget about this other parts. It's some statement that I have many distinct unitaries. Forget about. Now, how we prove it? So it's basically just repetition of the textbook argument from Nielsen and Chuang, and like in our lecture with Marcin, we actually probably gave very similar arguments. Right, but at some point you use just equidistribution, not Herr measure. Right, so we want to prove that with high probability, unitary has large complexity. So what we are going to do instead, we are going to upper bound the probability of the unitary having low complexity, okay? And we're going to upper bound by some delta, right? Yeah. Okay, so let me study unitaries of complexity at most R, okay? So what are those unitaries? It's relatively easy to at least formally write them down. So it's basically the union of all the of epsilon balls around all the unitaries that I got from circuits of size at most R, okay? So I have collection, like I have different sizes of circuits, and I'm summing over circuits of size R. Good. So now when I want to upper bound the probability that I have low complexity, I just need to compute measure of the set of low complexity unitaries, okay? Measure according to this measure nu, good. And now I basically use the union bound, so I'm gonna now like sum over circuit sizes and over unitaries with a given circuit size, and I compute the measure of now of a ball, right? So now you see where my assumption about equidistribution enters, because I can now use this approximate equidistribution property to upper bound this volume according to measure nu by volume according to Herr measure, right? But I also know that this volume is like scale is exponentially small with dimension squared, right? So I just put this in. Here I have just here I assume that I have a finite gate set G, and it has some size, right? So I just have some geometric progression at the end, so I can upper bound the probability that I have low complexity by just size G to the power R roughly, and something which is exponentially small with like epsilon to d squared. And now what I want is basically this thing to be smaller than delta. And I solve this inequality for R. And the right-hand side of that inequality in this result is basically solution for this R. Okay, so it's a textbook argument from Nielsen and Chuang, but at some point you use this approximate equidistribution property, but it doesn't change the scaling. Good. Okay, so I move now to the recurrence to Rafał question. Good.
Sorry.
Yep.
So
Good.
It's always probability is greater than this. So where's the saturation? Sorry.
Good. Oh, okay, so I have lower bound like this, and then the upper bound has basically the same scaling with d, or with the number of qubits, and with epsilon. So it's not, so this is the, to be fair, this is what we can prove, right? So we don't get quite at the maximal value, but we get the same dependence on exponential dependence on the number of qubits, so 4 to the n log 1 over epsilon, the regularization parameter. And okay, we have the series of the gauge sets. And the upper bound, that is just from compilation, has the form like this. For maybe.
So actually here D is D to the n.
D is 2 to the n. Yes, yes, yes. Yeah. Okay. Right, so the recurrence. So now, importantly, we are gonna keep track of the walker. We need to keep track of the walker after t steps. So, you know, what I mean by this is you cannot, for every fixed time large enough, you're gonna equidistribute. Okay, so for fixed time, you're gonna have very large complexity. So now to prove the recurrence, I need to keep track my random walker across many steps of time, like double exponentially many steps of time, as it turns out. Good. So yeah, I wonder where this recurrence happens. So what I want to show is that I will have actually no recurrence after, say, k1 steps with high probability. But also I want to show that after maybe 30 larger k2 steps, for sure I will get recurrence. That's my strategy. And to say, so I want to now put lower bound on this, k1, and upper bound on this k2 to like pinpoint my recurrence time with high probability. So this like basically lower bound on this k1 is relatively easy because I can just, okay, on high level, just repeat this reasoning, this upper bound, where here I don't do it for a single time, but for many times, and do another union bound. So that would give me, okay, that would give me that this k1 like with is like larger than 1 over like epsilon to, if I just solve, so you know I'm gonna just put here k1, solve again, and like this k1 would be okay, I'm like sketching, would be like this, okay, with, if I want to have still large, for quite large R, okay? So that's how you get the lower bound. But now this K2 part is much more interesting. And it's funny. Okay, so on high level, the reasoning is the following. So, like, we decide to look on our walker in stroboscopic manner. So instead of tracing after every step, I decide to trace every tau steps, where tau is equidistribution time. So I'm not after trajectory after every like full trajectory, but every tau steps. And now Janek intuition, and actually our intuition at the time when we were proving it, was as follows. So if we decide to look on this walker every tau, like every tau steps, it sort of behaves on scales epsilon as if in between we are just throwing high random unitaries, okay? So if I study some properties of the sequence u tau, u2 tau, u3 tau, and so on, its properties would be similar as if I had just w1, w2, w3, when I just take them at random, like in between I just apply independently high random unitary.
The whole space.
On the whole space, okay? And now let me, so you know, because when I want to show that with certainty my complexity went down, it's enough to show that, you know, to analyze this walk, like if I know that, if I could prove that in this walk, every tau steps, at some point I'm gonna go to low complexity, that means that for the original walk, I'm gonna also have low complexity. And now the situation becomes relatively easy when we have such a walk, because in every step we just choose at random, high random unitary. And what it means to have zero complexity means that I'm CV on scale epsilon equals 0 is, okay, it's small, okay. This is just the same as V being in the ball around identity of size epsilon, okay? So from probability theory, I have now a very simple situation. So I'm drawing things at random from the Haar measure, and I wonder after how many steps I'm gonna land in this ball, okay? And things are IID. So size of this ball is like epsilon to d squared, right? So after one over volume, I'm gonna surely land in this ball, okay? So that gives me upper bound on this K2. But since I just coming back.
So it's like, I mean, okay, so it's with respect to like this single V. You ask what is the probability that this V.
Yeah. So that's why, since I'm looking every equidistribution time, I have the upper bound, I have to multiply by, in this result, by T equidistribution.
1 minute to finish?
Yes, I'm basically, yes. I started with some delay though, but.
Yeah, so I took it into account.
Good. Okay, but this is the end, right? So that was the intuition for the recurrence. So to summarize, we studied complexity evolution of local random quantum circuits and complexity of stochastic local Hamiltonians. We use spectral gap property to assess after what time approximate equidistribution would happen, and this allowed us to pinpoint saturation, recurrence, and duration of recurrence. Right, and there are some pressing open problems. We would, like with Marcin and other people, would really want to crack the Hamiltonian evolution, say for random Hamiltonians, for example. This is just those techniques that we have now, they cannot be applied. One has to move beyond this. There is this notion of Nielsen complexity that is based on differential geometry. Would be nice to study what our results have to say in that context. Is there any relevance to black holes? I don't know. There are also other models of random quantum circuits or random unitaries that one can study, especially things like monitored random quantum circuits. We should discuss this at some point, Janek. Brownian SYK model, and yeah, I should maybe say that with Marcin and Michał, we have some results that for GUE evolution, so for highly interacting system, you don't have actually ramp and plateau, but you have sudden jump, okay, of complexity. Right, and I'm back, as many of you know, at CFT, and have some projects, and I'm looking for postdocs, students. Yeah, that's it on my end. Thanks.
Thank you. Thanks for this very nice talk. So we have time for questions.
So maybe about this relevance to black holes. So what's, because like, from what I've read in some papers some time ago, like you typically basically, like the people who consider this quantum black holes or whatever, like study CFT, they always plot this entropy as a function of time, and they always show that, okay, at the beginning entropy increases because you are creating black hole,
Yeah.
then it's maximal, and then it decreases because it evaporates. Yeah, so it's very similar to your plot here.
Right, but perhaps the timescales are I don't know.
They are
Yeah.
similar, I think, but then
No, the timescales are different because after linear time, it saturates
I don't
entropy.
remember,
Yeah.
But then you have a recurrence of your complexity. So
Yeah.
between them, I mean, you created this wormhole or whatever.
Yeah.
Evaporated and then it works.
No, but it's like whatever. Like so, I actually in the pandemic when we were analyzing this, like there was this there was this paper with meditations of Lenny Susskind, like, and he really identified with evaporation of a black hole. Yeah, that's but I really don't. I'm on the quantum info side here. Yeah.
So simpler question, maybe.
Simpler right follow-up, but you also have an upper bound, so it could be that it drops but never goes up.
Oh, no. It drops, but then you repeat the same process. So it's basically just repeats itself. Yeah.
So maybe it's because in this ADS CFT, is this space-time bounded or not? Because then it will be like bounced once again.
Yeah, that's a good question because like they typically, like the solutions of Einstein equations, they don't have any exponential scale there, but it was just like a hunch on the. I mean, I should say that I personally don't take those proposals extremely seriously, but they were fruitful from the perspective that, okay, people started to study those things, and there are some meaningful mathematical quantum information problems, but also on the side of complexity theory. For example, there was a beautiful paper by Adam Buland, Bill Pfefferman, Umesh Vazirani, that they basically identified that actually it's very hard to assess your complexity. Okay, and based on that, they were sort of arguing that this ADS CFT, if you take it seriously, this dictionary should be very hard, because on one end you can, size of this wormhole you can, measure and compute quite easily, but complexity you cannot. And there were like some nice complexity theory. So I just view this field as more like inspiration for some problems. Yeah.
Maybe I can add something
Yeah.
apart from these black holes. And so, do you think, what's your intuition? Can you generalize this approach to, like, say, instead of sampling with these random unitaries, we would have some correlations between next samples? That decays, yes? And then it should hold. If this decay of correlation would be like exponential or something.
Right, that's for example, like my collaborator Marcin, he's really, I'm obsessed with this problem, but he's, I think that's a nice.
So then you can say how fast the correlation should die for this
Yes,
result to hold, and probably it will be some exponential decay or something.
Right, and I should say that formally one can study some correlated random walks when you use random quantum circuits in conjunction with classical expanders. So you just can like formally, fast forward some of this random evolution by studying something from expander graph rather than like something every time. Yeah. So so I agree with your intuition, and yeah.
So, any more questions? I don't see. Okay, so then let's
Thanks.
take Michał again.